More IPv6. We'll continue with the IPv6 Snort plugin, presented by Martin Schütte.
Yeah, hello. Welcome to my talk on the next talk on IPv6. A little bit about me. I'm Martin Schütte, now working in Hamburg for a web consulting company. But talking about IPv6 and Snort, and to give you a little bit of context on this project, this whole implementation was done as part of my diploma thesis in 2011, when even then everybody was waiting for IPv6 and it didn't happen. And now we're still waiting, but I had the great opportunity to become part of a federally funded project in Germany to improve IPv6 security. We did some cooperation with companies, and I could research IPv6 and intrusion detection and write this plugin. And thinking about IPv6 and IPv4 and security, I get the impression that we are basically there where the IPv4 internet was in the 90s, maybe 94. The big players in networking were research and academic institutions. Everybody, or mostly everybody, knew each other. Basically, you trusted one another. You knew that the protocols weren't perfect, but it didn't really matter. There was no urgency to improve them because everything worked, everything was fine, people were happy. And then suddenly everything changed and lots of people got on the network, and you didn't know anybody, didn't know everyone anymore, and there were bad guys, and you had to do something quickly. And I think the IPv6 world has to repeat that experience, because the really big players are now also backbone carriers, but most of them are still in research or academia. There are relatively few players, they know each other. We all know about insecurities, but there's no real urgency to fix them. At least it looks that way. And we can't go on like this forever, because it will change and people will use IPv6. And then we have to secure it some way. And lots of the problems with the protocol derive from the context in which it was invented. If we look into the 90s, when the IPv6 drafts were written and the standardization began, this was a typical network device. You had a big workstation. It was heavy, you couldn't carry it around in your pocket. It was wired, everybody knew whom it belonged to. It was in some organization with a hierarchy. And you didn't have to worry about it. You knew which device it was. And nowadays, if we look around, as already mentioned in the previous talks, every one of us has 5 devices, maybe more. Even if we go to a customer, we carry 3 or 4 devices in our pockets with us around their firewalls and security measurements and everything. And there are small devices, there are cheap devices, and even from the vendor's perspective, if I buy a $50 smartphone, I don't really have any expectations of security updates. They are glad enough to sell it, not to support it for 10 years. And in the context of network protocol in IPv6, this shows this discrepancy because between the expectation and the reality. And it was the whole protocol suite seems to be designed in the 90s to solve the problems in the 90s. For example, this whole thing with multicast and solicited node addresses was designed to save interrupt time because CPUs were slow, interrupts were expensive, you want to avoid them. Don't use broadcast in a new network protocol. And IPv6 solved that problem, and now 10, 20 years later we don't have that problem anymore because it's all done in hardware, and even my network interface controller is probably more powerful than the main CPU was back then. The problem is this all gets handed down, the protocol gets more complex, and it accumulates all these little steps and improvements. And one other slide I like to take up from Enno is that we have these different generations of protocols in IPv6, which also make it very hard to analyze it. We have the original standards, then we have some first wave of RFCs that improve on it. Then 5 years later, we get a second wave of RFCs. It's really hard to tell, is the device IPv6 ready, IPv6 enabled, capable? Is it the latest IPv6 or is it something like from 10 years ago with known vulnerabilities? And especially in an enterprise context, you have hundreds of devices. They all have different implementations of these standards. That makes it really hard to just give any statement about the security. But after all, we are in 2014 and IPv6 adoption has to come. It is increasing over time and we are really running out of other options. So it will come. And we see yet another wave of RFCs. And if we think about from the perspective of an enterprise or telecommunication vendors, the question is, can we make this so secure that we can sell it to our customers? Because it's still one thing to be able, as a network operator, to secure your servers and your routers and your switches, which is hard enough. But if you sell millions of Wi-Fi routers to end users, how do you keep them secure? That's the biggest problem, I think. Yeah, and as we've heard before, there are lots of attacks against IPv6. Some of them you will find in any networking protocol, but some are IPv6 specific. And my focus here is mostly on auto configuration, network discovery, and the problem with variable header length. We've heard in the earlier talk that multicast is a very interesting topic, and other things are routing and the transition, but I won't go into details there. And the easiest form of attack is a local attack. On link local, every device is equal, and every device trusts one another, and it's way too easy to make a denial of service attack on a local network, because I can prevent any device, or maybe only a specific device, from joining this network. As soon as this device shows up, I just say, oh, that IP is already taken, that's mine. And then the device will select another IP, and I repeat the step. So it won't get any official IP address. Same goes for routing, middle attacks. My device can always act like a router, and the other devices on the net will trust it. Things are a little bit better with remote attacks. There are some concepts how you can do remote denial of service attacks with IPv6 protocol implementations. And so far there are two in the routing section that are really serious. One was this source routing, and the other one was a loop creation with automatic tunnel. They were, on the standards level, they were fixed because the specific protocols and options were deprecated, but who really knows what devices are out there and which device still support these options. Yeah, if you want to play around with the protocol, there are some nice attack collections. To my knowledge, the oldest and one of the biggest is the THC toolkit from Mark Heuse. It's based on different specific attacks and has lots of tools to drive these attacks in different networks with very few options. And you can check this is a long list. It got even longer over time. And one really interesting tool I want to recommend is this implementation 6. If you have any kind of program or network device, just use that tool. It will send all kinds of malformed packets or unusual packets, and you can see if you have some bad assumptions in your code that don't hold. For example, you don't expect many extension headers, but then you get a packet that has more than 100, and then you see how your tool reacts or how your firewall reacts. It's really interesting, or scary, depending on the device under test. Another collection is the SI6 network toolkit from Fernando Gont. He did a security assessment of different networking protocols, including IPv6, and wrote his own toolkit for that. So yeah, when you work with it, the approach is much more structured. He has different tools to test different protocol fields, like one tool just to set different flow labels and one for different address formats. But that is also a nice tool set to test different unusual conditions with your devices. And last, a pretty new one, because we just had the talk from ERNW and Antonios, and he wrote his tool Chiron, which is pretty young, so far a little bit limited, but I'm confident it will get more functions over time. And it is based on Scarpy, which is a really nice Python network library to build your own packets. I can also recommend that, so I included that. Yeah, and now I already summarized lots of attacks and lots of tools to do these attacks, and they are way too easy in modern networks. Like in this conference Wi-Fi, nobody prevents me from flooding it with some packets and routes and multicast groups. The question is, what can we do about it? And the list of countermeasures is really short. And I don't really have a good answer, but the general approach has to be the first step is always to visualize, to monitor what's going on the network. And even that is difficult enough for a new protocol, because there are very few tools to monitor IPv6 networks. You even have network monitoring tools that will show your IPv4 network in high detail, but completely ignore the IPv6 traffic. So it's really hard. Once you have your monitoring, then you can look for anomalous activity, for attackers, for flooding, whatever, and based on that create your filters. But actually, we are not even at step one, I'm afraid. When we start to write a tool to help us with this, there are many points in the network where we can start to capture traffic, to take decisions on blocking or non-blocking certain packets. We have different types of placement, from the router to the individual host, etc. And we have different layers of abstraction where we can write our software. It can be a standalone tool which just monitors and does something. It could even be an operating system module. There we would be sure to capture everything, but maybe that's too integrated to be useful. Or we can have an existing networking application, write an add-on for that. And that's obviously the path I chose, because there are already intrusion detection systems. They are quite well known and have been around for several years. And that's a really good place to add your own code. And that's why we chose Snort for this whole project. We also considered some other, especially Bro and Suricata, but we chose Snort after all because it provided a very nice plug-in API. And our reasoning was we don't want everybody to recompile their IDS, because that would be quite a barrier for entry. We wanted to be able, or we had the goal to just give a dynamic library as a plugin, and then everybody could try it out. And yeah, after all, that worked quite nicely. So that's the basis for the whole project. To give you a short overview of Snort, it basically has this processing pipeline. It starts with collecting packets from the network, usually with a PCAP or something like that. Then it decodes these packets. It does some pre-processing on them, for example, assemble fragments, or maybe even assemble TCP streams. Then it has the detection engine with your own custom rules. And based on everything that happened before, you can get alerts and logs and outputs. And depending on the mode you run it in, you can not only monitor it and have a log output, but you can also get back to your firewall and say, I want to block this packet. This is then the inline mode or the intrusion prevention system mode, whatever you might call it. That's not really in scope here, but that's also an option that you can say, I'm really sure this is an attack. I just want to block these packets. Yeah, and as a systems administrator, what you end up with is a pretty big log file where you have to get some information out. Yeah, so we go through these steps in the decoder. Snort basically does the same as an operating system does. It gets a packet from Ethernet, extracts some information, source and target address, obviously. Then it looks if it's an IPv6 or an IPv4 address and basically walks through the protocol stack to decode this packet. Does that for every single packet that comes in. And once it's done decoding, you get a really big data structure with all these different information attributes about this packet. That has one big disadvantage. It's slow. For every little ping, you do this decoding. But the advantage is once you have this structure, then everything in the system can work on that. It's very easy to write a small preprocessor that looks into these fields or write your own rules in text format that evaluate these fields and act on them. Yeah, and these rules look basically like these. The big advantage of this rule system, as far as I know, Snort was the first system to implement this back in the 90s. The nice thing is everybody who knows about networking, but not necessarily about programming in C or low-level C, can write their own detection rules for network attacks. So if you really find something like a buffer overflow and it's triggered by a certain kind of packet, then you can write a rule for that, restart your intrusion detection system, and then these packets will be detected. This is just an example, but it shows some of the nice features. You can use variables for your network, so it's already a customization to your local network. And you can say, yeah, like match TCP packets from to these networks, maybe only establish connections, some content. The rest doesn't matter here, but the idea is that, yeah, everybody who knows about these things can implement these rules without having to really program them into binary code. So this was IPv4. What about IPv6 support? Technically, all devices support IPv6 for years, and obviously, and of course, so does Snort. But what does that really mean? How far does this support go? It obviously does fragment reassembly, and it's really good at reassembling your UDP and TCP packets. So all your application layer rules and detection routines run. That's really nice because all your HTTP rules work immediately with IPv6. And the decoder gets better over time and warns about really severe problems like really wrong packet lengths or unknown extensions. But it doesn't go very far. For a long time, it didn't check the IPv6 extensions at all. Now support is slowly coming. Not all rule options from this text rule language support all IPv6 options. And there was no IPv6 specific detection. For example, this whole neighbor discovery process, from Snort's perspective, they were all ICMP packets and they were fine, but there was no higher level analysis of their content. So, like I said with the rules, if I have a rule that checks an ICMP type, for example, then I really don't know if that packet is an IPv4 or ICMPv4 or ICMPv6 packet. And that's obviously very problematic if I want to write rules to detect IPv6-based attacks on my network. I really couldn't write this because it could capture any IPv4, ICMPv4 packet as well. And as I already mentioned, if I only do application layers and protect my web server, that's all very fine, but not for the low-level stuff. So that confirmed our decision to write a plugin for that. And then the next question is, what kind of plugin, what kind of API do we use for that plugin? If we look into the system, the first way to customize Snort is by writing these rules. I already explained that's not enough. The next system is these rules can also be compiled into binary code by writing C code, loading them as dynamic libraries. That already gives you way more access than you would usually have, but it's still very limited because you have to do, this rule applies, it matches, so you can do something on it, or it doesn't match. But you can't do much more analysis or keep state or anything. So basically, the dynamic preprocessor RP is the more powerful API. It allows us to define our own rule options, like IP version. And we can also do something with the packet. And something really means everything. We can stop processing, we can change fields, we can keep state over the runtime. So that's really the way you want to go if you want to add completely new protocol to Snort. Starting with the rule options, as I mentioned, the rule language was quite limited and didn't differentiate between the IP versions. And so the first thing to do was implement new keywords to access all the IPv6 header fields. For example, if I want to check some flow label value, maybe the latest exploit going around uses a specific flow label and I want to detect that, then I want to write a Snort rule accessing the flow label. Or I want to check if a certain extension header is set. These are the first rules I implemented. The basic functionality from programmer's perspective is, I wouldn't say simple, but pretty straightforward. You define a handler for this keyword. This gets a callback, and every time a packet comes in and you have a rule with that keyword, your callback is called, and then you return true or false, depending on whether it has matched or not. And then the rule engine will assemble it together with all the other rules and check for it. For example, with the ping message, the ICMP v4 and ICMP v6, I added an IPv keyword, and so I can say depending on the ICMP type, ICMP type 8 is an IPv4 ping with the right protocol or the wrong protocol. And likewise with IPv6, I can say this is an ICMP v6 ping in an IPv4 or IPv6 packet. So that's a really simple use case that wasn't possible previously. To get one level more technical, this will be the evaluation tree built inside of Snort. As soon as an ICMP packet comes in, this will get evaluated, and if it reaches a leaf, it will check which rule it returns true and is applied. There's a basic list of these rule options. Nothing really new. As I mentioned earlier, I wanted to access all these fields, and especially I also wanted to access all hop-by-hop options and their values. And most of them have some comparison, so you can check what options they have, the number of options, etc. They're just very basic building blocks to write your own rules. And in practice, then you can check, for example, for this routing header, or if you get jumbograms in your network that isn't supposed to have jumbograms. Things like that. And the second part after this whole rule language is the preprocessor the preprocessor part of the plugin. That's where we want to go beyond that. We don't just want to access single fields in the packet, but we want to do a more abstract analysis of everything that's going on in the network. And there the analysis focuses on the network discovery protocol. We want to represent the network as internal state and see which hosts are in this network, which routers are in this network, Are there new hosts joining the network? Are there hosts that shouldn't be routers but suddenly act like routers, like in man-in-the-middle attack? So we follow all these router advertisements, neighbor advertisements, neighbor solicitations, and try to map the Ethernet addresses and the IPv6 addresses of all the devices and check if there's a consistent state and everyone behaves as they are supposed to. So the functionality is basically every IPv6 message is read into this module, and then we check for these different messages that change state. So a new router advertisement, a new router solicitation, there we see there's a new device. And whenever anything changes or anything is unusual, then we fire an alert. There are several configurations options for all of this. Most of them are optional and are just out of concern for memory usage or CPU usage. The really useful ones are the first two, because on every network I usually know my network prefix, and it's very easy. If I configure that, then the plugin can check for all other prefixes. Likewise, I usually have only one or two routers, and I know their MAC addresses, so I can really configure that. And it's really easy to check if any other device acts like a router, and obviously isn't supposed to do that. Depending on your network type, you may also know all your host MAC addresses, but that's already a very limited use case. You know that for a server network, but not for public Wi-Fi or something. All the rest are just optimizations, because we wanted to be able to run on very small devices and limit memory usage. So I won't go into them in detail. A typical configuration would be like this. As I mentioned, I have my network, I have my router, and that already allows me to do very useful checks. At one time, we have a certain list of alerts we can fire from the plugin. That's basically the summary of everything I told you, everything that's changing in the network state, or anything that's highly unusual. New routers joining the network, devices that shouldn't be routers, acting like one, prefix change, duplicate address detection started, something like that. Some more for completeness, we checked some protocol fields, for example, packets with multiple padding options. I don't know for sure if that's some kind of attack, but it's unusual and we can check it, so we just do. And if it's false positive, then we can ignore that alert. Another thing is a tester. That's really more for the development part of it, because it's really useful if you work with firewalls or intrusion detection systems, if you can take a TCP dump and read that into your device and then check the log output, because that allows for very easy functional testing of everything. It really saved me a lot of time to be able to have a TCP dump with a THC attack, maybe some flooding also, and be able to read that PCAP file over and over again and check if the plugin and Snort itself did what it was supposed to. Unfortunately, this only works on PCAP files, so it's too limited to be used in a real network. Continuing with another shortcoming of Snort, and to my knowledge all these IDSs, we have very limited options to visualize the output of this log file, because you run on a very low level, you have these packets and you have lots of log messages from them, and there are very few tools that really show you what's in there. For Snort, there was some infamous option to write logs to MySQL. So there immediately were some bad PHP programs to show them to you. You don't want to look into their source code, and they are quite old, and overall they don't support IPv6, because as in any good SQL schema, an IP address was represented by a 32-bit integer. And because there were a dozen tools that use this schema, there's no hope to ever update that. So I've basically given up to find a good output tool. But on the other hand, there are some good general purpose log processing tools. So if you want to do output, then my advice would really be don't write a tool for Snort, but use an output plugin that makes some structured logging. And you get all the file data, maybe with Snort with that unified log format, or if you use Suricata, there's a new Eve output format that outputs JSON. And that's a good basis for all kinds of other tools. Especially this is a Logstash Kibana screenshot. They're just general purpose logging tools. They read in JSON data or structured data, save them in Elasticsearch, and then let you create your own customized dashboard based on that. And this is so advanced nowadays that it's easier to use this general approach than to write your own Snort output formatter or maybe your own Suricata output formatter. It just isn't necessary anymore. Yeah, some other options which probably show that it has an academic background. We thought about performance a little bit. And in theory, this whole ND tracking and keeping state of the network could be expensive. It could put us, make us a target for denial of service. If you have an intrusion detection system and you want to detect denial of service attacks, then your system shouldn't be the first one to panic and run out of memory. But in practice, that didn't turn out to be much of a problem because all these stateless checks already use the Snort decoder. And the state itself is pretty small and configurable. And we even ran this whole suite on a small Beagle board we could plug into our network. The obvious problem is if there is really a denial of service attack, then it will throw away old entries, but it won't run out of memory itself. One last interesting thing, maybe appropriate for DeepSec here. During development of this whole plugin, I had to dig deep into the Snort source code, and I found some interesting bugs in there, which basically show how major commercial security software is written and maintained, I think. I have to prepend, this was some time ago, it was in Snort 2.9.0. The critical ones were immediately fixed, the not so critical were fixed over time. I think in 2.9.5 most of them are gone now. But for me it was really interesting. The first one I saw with this THC implementation 6 tool, because it was one of the first things I did. I just started it against Snort and immediately the system stopped. And it turned out that I have some more details about that if you're interested, but I don't want to read source code to you. But the basic problem was Snort iterated through all the extension headers, and it had a limit of 40. And once you had that 40, it would iterate again, but it wouldn't increment the length counter, so it wound up in an infinite loop. Not really something you want in a software that's between the internet and your internal network. And it was way too easy to do a denial of service to completely stop your firewall or intrusion detection system. The other things is really small stuff in comparison to that. We have a wrong endianness in the IP version header, or something under certain conditions, these ICMP checksums are computed differently, and that wasn't considered in the source code. The general impression I had was that it was programmed by specification. Somewhere along the time, someone said, yeah, we have all these nice IPv4 functions. Now we have to port them and support the same functionality for IPv6. And we give someone the specification and he has to implement them. And all the APIs were there, but I had the impression nobody really used them. Otherwise, it would have you really notice if get IP version returns the wrong value because it didn't consider endianness. Yeah, likewise, something routing headers, frag bits, all these small parts. Not really serious, but yeah, kind of strange for a big network security suite that doesn't really support a new protocol. Yeah, I have lots more of source code. If you're really interested, come talk to me afterwards, but I won't show it here. Conclusion of everything. Yeah, biggest conclusion, it worked. It was, after all, possible to add extensive new functionality to Snort just using this plugin API. So that's basically why I like all tools with plugin APIs, because they allow you to do so much more than the authors intended. It enabled us to write some IPv6 specific rules for this language. And especially one of the earliest targets was we were able to detect attacks from the THC toolkit. That was our big yardstick with the most common attacks and the one most widely spread, and we wanted to find them. And that worked pretty good. Yeah, so that's the good news. The bad news is if you're on a linked local network, then your real problem isn't IPv6 and this neighbor discovery. Your real problem is an insecure Ethernet, because as long as any Ethernet device can use any address, it doesn't really matter if you're, so Ethernet on layer 2, it doesn't really matter how secure your layer 3 is if everyone can just plug in any device or use the Wi-Fi and get access and can impersonate everyone else. That's one thing that makes it really hard to lock down public networks. Yeah, that's a limitation, but on the other hand, I really think that having a plugin for a widespread security system is a very easy way for network administrators to add these IPv6 checks to get some visibility of what's happening on the network. Because it's really hard, you have this network and you enable new addresses, but you don't really know what's going on. And this offers you a chance to get some feeling for it. How many attacks, or are there attacks, how many traffic is there? That's, I think, the big opportunity for that. Yeah, so if you're interested in it, you're always welcome to contribute or just contact me with questions. Everything is available as source code. I finally found the time to build a Debian package out of that, but I really had my problems with auto tools and the packaging system, so it may not be that perfect. Anyway, on the small project page where you can find the article and the diploma thesis on it, so everything's online, including these slides. I just uploaded them to SlideShare. So you find them online as well. And last but not least, I want to thank my employee who basically sponsored my time and allowed me to be here. Yeah, and that's it.
Thank you, Martin. We have time left for questions. Anyone?
First point, thanks for mentioning the people when you use their screenshot. That's good. So I'm Eric Leblanc, one of the Suricata developer. So I'm not happy you choose the Snort to develop a plugin on that. Just to stop that, main point would be that if you had done the same work on Suricata, it would have been mainstream or not usable as a plugin.
The audio is really hard to hear.
Sorry. Sorry, my point is you did not choose Suricata for your development. I understand the point on the plugin infrastructure, but my point is if you had choose Suricata, but maybe your code would have been now upstream, so accessible for everybody.
Yeah, that's really a problem. I contacted SourceFire with that, but it kind of was lost. So it didn't go upstream. I didn't pursue it for much longer. Maybe I should have. But that's a problem. And yeah, I can't really say much more about that.
Any more questions? We still have time. Okay. Then let me pose a question, please. Did you find any specific operating systems that particularly behaved badly?
No, not really. I developed everything under BSD, tested it then under Linux. And yeah, most of the lab tests were done with Linux and Windows. Some of these THC tool attacks are specifically, or not specifically, but they are documented to work against Windows or Linux or some BSD variants, but that's not limited to Snort. So some IPv6 vulnerabilities in general are inside network stacks of specific vendors. At that time, very interestingly, was Microsoft, obviously, with XP and Windows 7, because it's a big target. But in my development, it didn't matter that much. I found no difference.
Okay. So, if there are no more questions, thank you, Martin.
Thanks.